Login acceptance.
Yeah, so I think we can start now. So welcome to the mistakes and trade-offs, optimizing the hot path when premature optimization becomes an early optimization. Uh, I am Tomasz Lelek. Everything works? Yeah, so I'm working at Data Stacks, with doing some things with Cassandra. I'm published author of Software Mistakes and Trade-offs, Making Good Programming Decisions for my mining publisher. Previously, I was working at Allegro Group. I'm also a technical trainer at Bottega IT. There was also a couple of other talks from guys from Bottega. And you can find me on GitHub, Twitter, and LinkedIn. So there is an old computer science saying that premature optimization is the root of all evil. You know that, right? And it has a solid background because it's accurate for a lot of use cases. Without any input data about expected traffic and SLA, it's hard to reason about your code and its required performance. Optimizing random paths in your code in such a situation is like shooting in the dark. You will complicate your code without a sane reason. So let's start by finding and analyzing when premature optimization is evil. Often, when we are writing our application's code, we don't have much input data regarding its expected traffic. So in the ideal world, we would always have the information about the expected throughput and maximum latency requirements. But in reality, we often need to follow a more ad hoc approach. We are starting by writing software that is maintainable and easy to change. However, as we are writing the code, we don't have strict performance requirements often. In such a case, optimizing the code upfront has too many unknowns. So when optimizing the performance of some code path, we are often increasing its complexity. That's often the case. And this additional complexity arises from the fact that we are changing the code to be performance optimized. Sometimes we need to write parts of it in a specific way. In those parts of the system, we are trading off its performance over complexity. It may be code complexity, but also maintenance or system complexity of the components that we use in this system. And without the input data about the traffic, it may turn out that the given code is not impacting the overall performance of our main workflow. And because of that, we introduce additional complexity without the benefit of increasing the overall performance of our application. And another pitfall we might encounter is optimizing code based on false assumptions. So let's see how it's easy to make this mistake. So let's consider a simple scenario when we have a simple account entity. This is at the top, for which we are building our processing pipeline. So it's a very simple code in Java. And this simple code is using the Stream API, and it hides quite many performance optimizations for us already. So the stream abstraction works lazily. It means that it will execute the filter operation that checks if the account ID matches the argument as long as there is no account found yet. And let's clarify the usage of findAny versus findFirst. So those two methods are available on Stream API, and they are often used in wrong context. So the laziness is achieved by using findAny here. This method will stop processing when any element is found. If we used the findFirst method, it would have the same behavior as the sequential processing approach. If this processing is split into parts, then findAny may perform better because we don't care about ordering of this processing. However, using findFirst will mean that the processing must be done in order, and it slows down the processing pipeline. And this difference becomes even more important when we will switch to parallel streams. So we created this code as the first approach. It is important to know that we don't have any performance information at this stage. The list of accounts that we are processing could contain a couple of elements, but it can also contain millions of elements. And without this knowledge, it's hard to optimize the performance of this specific processing. For the low number of accounts, our code will be good enough, right? For millions of elements, we may consider splitting the work into different threads. The one solution will be to create those threads manually, split the work into batches, and submit it into multiple threads. We can also leverage existing mechanisms that hide the creation of threads and split the work, such as parallel streams. So let's assume that we are deciding to introduce performance optimization to our processing code, and we notice that processing works in one thread. We use normal streams. It means that we cannot split work and execute it concurrently, leveraging all cores of our CPU. And one of the possible optimizations that we can do is to use the work still algorithm. We would need to split the work into n independent stages, and all input accounts will have n elements in it. Firstly, we split it into half, into two threads. At this point, two threads will be responsible for processing half of the n accounts. Secondly, our code should do another split because not all threads are utilized. And the work will be split into 4 of n accounts. And at this point, every thread will be able to start the actual processing. The split phase should split the accounts into as many parts as there are available cores or threads. So we have parallel stream, right? So the parallel streams method will split the work into n parts, and it will use the internal fork join thread pool with a number of threads equal to the number of cores minus 1. We can also tune it, but that's the default. And it looks simple, but it hides some complexity. So what are those hidden complexities? So the parallel stream method will split the work into n parts. It will use this fork join pool. And the most important change is that our code is multi-threaded now. Before that was single-threaded. It means that the processing should be stateless. We shouldn't modify any state from any processing method, for example, filter or map. Because we are using a thread pool, we should monitor this thread pool, its usage and utilization. So was it worth it? So another hidden complexity that the work still algorithm has its place is the work of splitting the work, the phase of splitting the work. And this phase takes additional time, adding performance overhead to our code. The splitting phase overhead can be higher than the gain that we get from making it parallel, right? So because we base our optimization work on false or no assumptions in this case, we cannot reason how this code will perform on production. To validate if our performance optimization was efficient or not, we should write a performance benchmark validating both methods. So we assume that the processing would work for n accounts. Let's assume right now for this exercise, it will work for n accounts where n is equal to 10,000. And regardless if this number is based on the empirical data or our assumption, we should at least write a performance benchmark to validate if our optimization is valid in this context. The benchmarking code will generate n random accounts with IDs from 0 to 10,000. We can generate a random string using the UID class. The fork parameter states that all tests should be run in the same JVM. We will be using the Java micro benchmark harness, JMH, tool for benchmarking. And before the actual benchmarking logic, we should run a warm-up that will allow JIT to optimize code paths. It is configured using the warm-up annotation at the top. We will execute 10 iterations of measurements. That is good enough for the simplest scenario. The more iteration, the more repeatable results. And we are interested in the average time that the method takes. And the results will be reported using milliseconds time unit. So let's take a look at the benchmark initialization logic. So the baseline method will execute the first version of our accounts finder logic, this normal stream-based, and the parallel method will execute the improved version that is using parallel stream. That's the only difference. So let's execute the benchmark. You can try it on your machines, but I will show the results from mine. So let's execute it and see the results. So please note that the exact number might differ on your machine, but the trend will be the same. So when we execute the benchmark logic, we will notice the performance of both solutions is almost the same. One of the examples run output would be like this. So you can see it's almost the same. The parallel processing might be slightly slower even because of the split overhead needed before the actual work. If you increase the number of accounts, you might start noticing that the parallel version is slightly faster and faster. Overall, the difference between both solutions will be negligible in this context. The parallel solution's performance results do not justify adding the additional complexity that arises from the fact that we are using multi-threaded solution. However, the code complexity doesn't increase whether you choose parallel stream or standard stream. It's important here that the complexity is hidden in the internals of the parallel stream method. You may not be even aware about this complexity at the first glance. So what are lessons learned from this simple example? So we assume that the code will be called for a specific number of elements. And in such a context, the second version of our code does not perform better. The problem is that the numbers used to conduct the test were a guess, right? In a real-world system, it may turn out that the number of elements that we will process will be substantially different. It can be higher or lower. It means that we will have more empirical data that can be used to optimize the code, but this time based on real-world assumptions. In that case, we can get back to the optimizing the code, but this time with correct numbers and adapt benchmarking logic. If you know upfront that the accounts will grow over time, you need to adapt your benchmarking logic. Once you hit some threshold, you will notice that parallel stream will perform better than standard version, and in such a case, it's not premature optimization anymore. So we looked at one aspect of the input information needed for useful performance optimization. In real-world systems, we have a lot of code paths. Even assuming that we know n for all input processing, it might be not feasible to optimize all of those paths in our system. So we should know how often the given code path will be executed to decide if it's worth optimizing. There are code paths that are executed very rarely, like, for example, initialization of our application components. However, we have code paths that are executed for every user request. We'll be calling this code the hot path. Optimizing code on this path is often worth doing, and is resulting in substantial performance improvement of the overall system. In the next part of this presentation, we will learn to reason about this hot path in our code. In the previous part of this presentation, we saw an example of optimization based on false assumptions. One of the essential data characteristics that are very useful when optimizing your code is knowing the number of elements, this n. It may be the number of requests per second, number of files you need to read, and so on. As we all know, an algorithm's complexity can be calculated by knowing what is an input number of elements, n in this case. We can pick a proper algorithm, but we can also estimate memory usage. And knowing this n is vital, but not all code in our applications has the same importance in real code on production systems, right? For example, let's consider a simple HTTP application that may have different endpoints executed more or less often. So the first process request endpoint is exposing the main functionality of our application. It is executed for almost every client call and does the main work. Let's assume that this endpoint is executed by our clients 10,000 times per second. We also assume that the n for both endpoints is calculated based on the empirical data or the SLA that our service will offer. So the data that we are using is based on assumptions backed up with actual data. On the other hand, we have a different method that does more heavy work. The modify schema manipulates the data structure in the underlying database that this HTTP application is using. It is called very rarely because changing the schema is not a common task that clients are executing. So once the schema is changed, it will stay in the same structure for some time. So let's assume that we measured the 99th percentile of latency for both endpoints. That is, 99% of requests are faster than the specific number. After some time, we'll get the results concluding that P99, this percentile, latency for process request is equal to 200 milliseconds. For the modified schema, P99 latency is equal to 500 milliseconds. So if we looked only at those measurements without the context of the number of requests per second, we can conclude that we should start from optimizing the modified schema endpoint. When you add the context about number of requests, it is easy to calculate that optimizing the process request endpoint will give us more overall resource and time savings. So for example, if we will be able to reduce the P99, the latency that we have for process requests by only 20 milliseconds, so 10%, we'll get the overall reduction of latency equal to 200,000, right? Because we can multiply number of requests per this 200 milliseconds, then subtract the value after optimization, and we'll get the overall reduction of latency on our system. And this is only 10% decrease. And however, if you will optimize the modify schema endpoint twice, so this is very hard, to 250 milliseconds, we'll get a substantially lower overall latency reduction that is equal only to 2,500 milliseconds. And it's obvious that often optimizing by 10% may be easier than optimizing twice, right? So based on that calculations, we can conclude that investing time in optimizing the endpoint that is called more often will result in 80 times more savings than optimizing the endpoint that takes more time to execute. The path that is executed for the majority of requests is called a hot path, as we know, and finding and optimizing it is a crucial aspect if you want to optimize the performance of every application. It turns out that in real-world system, this pattern of unevenly distributed traffic between code paths in our application is happening very often. There were a lot of empirical studies that ended up as a Pareto principle that we can simplify thinking about our systems. So let's take a look at this principle in the next slide. There were studies of multiple systems, organization, work efficiency, software systems that found very interesting characteristics for most of them. And we will analyze it in the context of software systems. It turns out that the small fraction of code delivers a substantial proportion of the value produced by our software. The proportions that were detected most often were 80% to 20%. It means that 80% of the value and work that our system is doing is delivered by only 20% of our code. And it could be presented by this graph. If we had a linear behavior, it would mean that every code path in our code has the same importance. In such a scenario, adding a new component to our system would mean that the value delivered to our clients increased proportionally. In reality, every system has a core functionality responsible for the core business and provides the most value, and the rest of the functionalities that are not crucial, such as validation, handling edge cases, handling failures, do not produce much value, business value. However, they require 80% of the time and effort to build the whole system. Of course, the actual proportion will differ depending on the business domain and system. It may be, for example, 30 to 70 or even 10 to 90. And the actual number is not important. What's the most important is the lesson from this characteristic. So we can conclude that optimizing the smaller parts of our code base will impact most of our clients, this 20% in this example. So when creating a new system, we should have SLA requirements with an expected upper bound of traffic that our system can handle. Once we have those numbers, we can create performance tests and that are simulating real-world traffic. So, for example, let's assume that our service needs to provide the SLA for handling 10,000 requests per second. The average latency for requests is 50 milliseconds. If you want to examine such a system by the performance tool, it's essential to set a correct number of threads that this tool will use to execute the request to a system under stress. If you will pick one thread, we will be able to run at most 20 requests per second, because 10,000 milliseconds dividing by 50. Such a performance tool setup won't allow us to examine the system SLA because we need to handle 10,000 requests per second. However, once we know that one thread can handle 20 requests per second, we can calculate the total number of threads that we need. We can divide the expected number of requests per second by the number of requests that one thread can handle. So we have 500. It will tell us that we need at least 500 threads to saturate the traffic. Once we have that number, we can configure our benchmark tool accordingly. If the stress test tool is not able to create that many threads on one node, we may divide that traffic into n stress test nodes, where each test node handles a portion of the traffic. For example, we may execute requests from our four stress test nodes. In that case, each of those nodes will need to execute requests for 125 concurrent users. And please note that this calculation may be a bit different depending on the performance tool that you use. If your performance tool is using an event loop, so non-blocking I/O, you may be able to execute more requests from this one thread. And in such a case, you need firstly to measure the number of threads that one thread can handle and adapt the rest calculations to it. Finally, you should create a bit more threads that calculated because the calculations are based on average latency. And then there might be still some outliers that will slow down the concurrent threads. To see how many outliers we have, we can look at the latency of higher percentiles, like P90, P95, P99, and so on. And due to that fact, we can multiply the total number of threads needed for an average SLA by some factor, like for example 1.5, to have some extra threads, allocate them in the case of temporarily slowdown of a system under stress. The next step that we can do is measure critical code paths regarding the number of invocations and the time that it takes. By having those numbers, we can detect the hot path and calculate how significant performance gains we can get from optimizing a small part of our code. Thanks to the characteristics of most of the systems that follow the Pareto principle, by optimizing our hot path, we can impact and deliver improvements for the majority of our clients. We will apply this framework for optimizing a system that has a defined SLA. And in the next part of this presentation, we will build and understand the system and its domain, and we will try to optimize the hot path of it. Yeah, so let's say that we have a WordService that has two functionalities exposed under two API endpoints. The first functionality that it offers is getting the word of the day. It calculates the offset specific to the current date and returns the word with an index equal to index to this offset. And the second functionality is just validating the word. The user is passing the word as a query parameter and scans the dictionary for its existence. it returns the information about its existence in the response body. The next couple of slides of this presentation will have a lot of code, and we don't need to dig deep into it. Yeah, they are not just enough to understand the service basic functionality. So the WordService is a core component of our system based on WordService interface. The get word of the day method does not take any arguments. It just returns the correct word of the day, and the word exists method takes the word that should be checked and returns if it exists or not. And the first implementation of the word service is not trying to do any performance optimizations, as we don't have any numbers regarding SLA or traffic yet. So the core functionality for getting word of the day is calculating the index for a given day. The logic is simple, as it uses year and day of the year plus a multiplying factor to have a better distribution of returned words. And we are picking the multiplying factor to be equal to 100, but it can be any arbitrary number. And the logic for calculating the word of the day, do you see that? I will. Yeah, the logic for calculating the word of the day is leveraging the scanner class that allows us to scan the file lazily. And as long as we want the next line, we need to call the method that retrieves it. And once we are done processing, there is no need to load more lines. And the logic is quite simple. It iterates over the file as long as the line number index, denoting the day's expected word, is not found. As long as there are more lines, we are executing our logic. Finally, if the current processing index equals the index for the expected word, we can return the word and finish the processing. Please note that at the end of processing, we are handling one edge case. If the index of the word of the day is too high, no word for today is returned. And last piece of code that we need to see during this presentation. So this is the second business functionality that our service is delivering, is validation if the specific word exists. The logic for getting this information is similar to word of the day, but in that case, if the word does not exist, we need to iterate over the whole file to the end. The word exists method tries to find the word passed as an argument. If the line loaded from the file equals the word argument, we can return true. It means that this word does not exist. Finally, if the word was not found after iterating the whole file, we are returning false. The logic for word exists is not optimized, as we did not define the SLA yet. We don't have any performance test to find the performance of the current solution. Finally, we can expose our logic under the API endpoints. Both functionalities are exposed as HTTP endpoints. I will not show the code here because it's pretty simple, and if someone wants to take a look at it, I will give a link to the full source code. So we have the code. Let's assume that our traffic estimation and SLA states that the word of the day endpoint will serve 1 request per second. On the other hand, the word exist will be called more frequently, 20 requests per second. Straightforward calculation will show us that it even exceeds the value from the original Pareto principle, 20-80. It means that the word exists functionality serves 95% of the user's requests. Before we start optimizing this endpoint, we should create a performance test for both endpoints to give us latencies. By knowing both numbers of requests and latencies, we can calculate the overall benefits of optimizing one functionality or the other. And I will show an example using Gatling to performance testing. So we want to model two performance test scenarios. The first one should target word of the day endpoint and execute 1 request per second. And the simulations using Gatling are written in the Scala programming language. Every simulation needs to extend the simulation class. Scenario for getting word of the day is straightforward. We need to execute a GET request for a given endpoint. Every request will be executed in the context of this HTTP localhost words URL. And if you want to deploy the Word application to a separate server, of course, we need to change the URL. And our endpoint accepts and produces application JSON. The benchmarking scenario executes the GET HTTP request on the word of the date endpoint. We are expecting the results to be equal to 200 HTTP response code. Any other code will be treated as error. And the second scenario is similar, but the HTTP GET request needs to send the word to validate as a HTTP parameter. Because of that, we need to feed the scenario with the words that we want to validate. And we can have an example CSV file that contains those words. Please note that we have the word bigger from the beginning of dictionary. We also have word presence that is in the middle of it. And finally, we have a zoo word that resides at the end of dictionary. And besides that, we have two words that do not exist, and they will trigger the full scan. And the words.csv file will be used by the validate scenario and pass as a query parameter to the API endpoint. The feeder will fetch words from words.csv, executes them randomly, and finally the scenario is executing a GET request with the word query parameter. And we need to do a setup of a traffic according to the SLA that we defined. So once we have defined scenarios, we should inject them to the execution engine and specify the expected traffic. The first scenario is executing 1 request per second, as we remember. The validate scenario responsible for 95% of the client's requests is executing 20 requests per second. Yeah, we can run this. Also, you can do it yourself when I share the code. But let's take a look at the example results. So the word of the day scenario performance looks like this, seems good enough. Our request of the word of the day endpoint succeeded below 800 milliseconds, and the P99 latency is equal to 361 milliseconds. However, let's now take a look at the results for validate words endpoint. The endpoint executed the majority of requests. The majority of requests have latency higher than 1200 milliseconds, and the 99th percentile is almost 5 seconds. So by looking at those both results, we can see that word exists performance is problematic. Fixing it will impact 95% of our customers. There is no need to premature optimize the word of the day, as the performance is good enough and impacts only 5% of our users. And we can calculate that. So let's calculate the performance impact of both endpoints using the formula from the beginning of this presentation. So the word of the day latency was 360 milliseconds, but we have only 1 request per second. And on the other hand, the word exists is almost 500 milliseconds. Sorry, 5,000 milliseconds. So we can, using that, we can calculate the word of the day is responsible for less than 1% of our service requests handling work. So once we have those calculations, it's obvious that we should focus our optimization efforts elsewhere. The word exists logic takes 99.7% of the total workload of our system. And once we know that the word exists is problematic, we need to get information from our code's lower level. So we need to understand what parts of the code path takes most of the processing time. We can get this information by measuring the code that is on the hot path. And let's see how to achieve that. So initially, the code for validating if the word exists was simple and we had no optimizations. We didn't know at this point that optimizations may be necessary. And now we have an input number regarding the number of requests that our service will handle. The performance tests show that we have a problem with latencies on the endpoint that serves 95% of our users' requests. And the Gatling tests were black box, meaning that we get information on how the specific endpoint performs, but we don't have any internal information about the most time-consuming part of this system and of this code path. And we can measure this code using metrics. So the word exists method contains two main functionality. The first one is loading the file containing those words to check. And the second one is scan phase that tries to find if the actual word does exist. And we can wrap both stages into separate timers to measure every invocation of those methods and give us more detailed information about their performance. We will create two timers. The first timer will measure the time that loading of the file takes, and the second timer will measure scan time. How long does it take to find if the word is valid or not? And the timer will be executed for every operation and will give us percentiles, average, and also number of invocation. You can measure your code at any granularity level that suits your needs. And measuring every code path also might impact the processing logic's overall performance, so we should be also very careful. And once our logic is optimized, we may decide to just remove these measurements. So after the Gatling tests will finish, we can take a look at metrics. They are exposed under metrics endpoint most often. And we can find a section that is dedicated to load file operation, and it will have data for percentiles. We are most interested with 99th percentile, so let's take a look at it. The results here are reported in seconds, and we can see that 99th percentile of the load file action is equal to 7 milliseconds. The load file operation is not causing the performance problems that we detected using the Gatling tool. We also have a count showing the number of invocation of the specific code. And using that, you can compare different code paths and see when most of the time is spent. It may be handy if you don't have predefined information about expected traffic or SLA. So if you have that information, you can use the metric to validate your assumption. In such a scenario, you can deploy the application to production with metrics and calculate which code paths were invoked most of the time. By having this information, you can detect the hot path and focus on improving the performance. And we have the second timer. So first one was validating load file, and right now we have the second phase of our processing. And we can see that 99th percentile is almost 5 seconds. So it seems that we found the underlying cause of our performance problems, and the scan operation takes a long time to execute, and it also takes the most of the processing time. Once we detected the underlying cause, we can start optimizing the hot path that needs these optimizations. So in the next slides, we can optimize our application's hot path that we detected and validate if our improvements result in better performance. So we might consider also implementing those JMH tests, asserting that I shown for the stream example, asserting our code's performance at the lower level and getting faster feedback after our changes. The faster feedback would be possible because we don't need to run the whole Gatling performance suite every time we experiment with our alternative implementation. And I will not show JMH tests right now. It will be too long, but you can get back to it when I share the code. Once we know where the problem lies, we can start optimizing the word exists code path. We need to reduce the time spent on the scan phase. Let's assume that the words file that we are using for checking word existence is static and does not change. This assumption is very important because in the context of our logic, it means that once we check if the word exists, the value will not change in the future. So we can implement a solution based on the cache and measure its performance. We need to construct a cache that will call the existing word exists method if the given word is not present, and we can set the default eviction time to some timeout. It can be, for example, 5 minutes, and it can be adapted once we have more data about production traffic distribution. We are constructing the cache where the word is a key, and the information about its existence is value. In this example is using Guava library. When the specific word was not accessed by the eviction time, it will be removed from the cache. And at this stage, we are ready to run the Gatling performance tests again. And let's take a look at the results. So we can see that the performance of our solution increased substantially, and latency 99 percentile is equal to 65 milliseconds. It's almost 80 times faster than the initial hot path logic. And once we perform our optimization, we should recalculate the impact that the specific parts of our code take on the whole application. So our P99 latency was reduced to 65 milliseconds now. We can use the same formula as before to calculate the performance impact of the word of the day and word exists logic. So the word exists traffic is 20 requests per second, and latency is equal to 65. So it gives the total of 1,300 milliseconds taken to execute those requests. And the word of the day has only one request, but this one request takes 360 milliseconds. So the total time to execute all requests for this endpoint is equal to 360 milliseconds. So finally, we can calculate the percentage of the traffic generated by both endpoints, and we can do it by calculating the traffic for the word of the day. So our calculations show that now that the word of the day traffic is generating 21% of the workload on our system, and the word exists is responsible for 79%. And as you remember, we reduced that from 99.7%. And also, it means that the word exists is still responsible for the most of the workload. However, as we calculated before, it impacts 95 of users' requests. And after our optimization, the word of the day that affects 5% of the users' requests take 21% of the processing resources. So if we seek further optimizations, we should calculate the possible time saving using formulas from this presentation. So let's assume that we can further improve the performance of both endpoints by 10%. For the word of the day, it will give us 36 milliseconds of time savings because we have only one request per second. So 10% from this one total latency will be 36. And improving the word exists performance by further 10% will give us 130 milliseconds of time savings because we have 20 requests per second. So, however, if it may turn out that optimizing the word exists performance by further 10% is infeasible or hard to achieve. We can calculate that only optimizing the word of the day by 40% will give us more time savings than optimizing the word exists by 10%. So you need to rate yourself what option is more feasible or easier. Yeah, and that will be it from my side. So if you like this presentation and approach, you might also check out my book. Here is the link. If you are interested, you can use the discount code here. I will also share the slides afterwards. Yeah, and here is the full code from this presentation. So the whole application that I've discussed, all benchmarks using Gatling, JMH, so you can run it yourself and test this approach and experiment with implementation yourself as well. And yeah, do you have questions regarding approach and solution? Sure.
One question maybe. Do you know any other libraries or frameworks that we can use to do such tests, like different than Gatling? Can you recommend something else?
Yeah, sure. So yeah, I've shown two types of tools. One was those more black box, higher level. Example was Gatling, another was those JMH low level tests. And higher level, yeah, so it depends on the type of application that you want to test. But for example, at DataStax, we have a tool that is called dtest that is responsible for testing the data layer. I think also all databases providers have own toolkit. So for example, Yahoo has nbench, NoSQL bench. This is shortcut, and that's a great tool and has like a lot of interesting scenarios depending on traffic distribution. Because here I shown very simple example of just two scenarios. But yeah, also it's all tools that I'm talking about are open sourced and free. So for NoSQL bench, also you can check out DataStax repository, and we have like 30 scenarios from different traffic patterns that you can use there. So yeah, but Gatling is the most UX like user friendly in the fact that it's easy to understand and write simple scenario. But for most, yeah, for more complex one, it may be hard. Also, there is a tool in there are some tools in script languages. I don't remember right now, but I can like tell you later. Check it out.
So you showed the example where the hot pass was really like understandable which one, but if you just switch the percentage of the requests, so we will have almost the same like almost the same results for both passes. In this case, which pass you will identify like a hot pass, and maybe one of them, even if it looks like it's reasonable to optimize it, maybe time consuming of optimizing this pass will take really like 10 times more. How to define which pass to optimize and how many time it will take?
Mm-hmm. Yeah, so as if I understand the question correctly, there's a scenario that we have two paths that has almost the same latencies and so on, right? Yeah, so I think the good approach would be to analyze both of those paths and take a look which one is just simpler to optimize, right? Because both of them will give you the same time savings, right? But you can also use those simple calculations because even if they have the similar latencies, if the one has more requests, then this will be the it will yield better results. But what's easier to optimize, I think. But
Maybe we should use some kind of, for example, risky zones. For example, in your example, it was like it's the same level of necessity for a user. But if it will be like one of them is more risky and brings us money, and other one no, should we think also about business?
yes, yes, I think that's the question of if the change is risky, right? But if you like assuming that you have good CI, good testing infrastructure, the riskier path will be tested better, I think, right? Because it brings more money. So maybe it's not riskier regarding some changes, right? I mean, if for example, in database, when we have a hot path that is executing requests from client to server, that's the path that is tested in the best way, right? all possible ways, end-to-end tests, performance tests, and everything. And the other paths are maybe not so well covered in tests. So maybe in the end, this is even less riskier, right? I don't know. Do we have? Sure.
What approach would you recommend to choose the test data to sample reproduction traffic? Code it somehow?
Yeah, it depends if you what kind of a software you are creating. If you are in one business domain and you have data about the traffic, like for example, in an e-commerce that I was working, the traffic will be of most often the same, right? So the basing it on the production flow will be reasonable. And on the other hand, if you have software as a service that you are not able to predict all patterns upfront, then you need to validate against very different patterns, right? Maybe, yeah, maybe you take from customers that will agree on sharing the traffic. Like, for example, Google will have different patterns like than Amazon and so on. But if if you are able to replicate some production traffic with anonymization and so on, that's a good. I think that's a good starting point.
What is the maximum percentile which you are taking into consideration during defining SLO or SLA? I mean, is it 99 is the maximum, or you are taking some higher 99.90, 90, 90?
Mm-hmm.
From your perspective.
Yeah, so I think it also depends on the contract with the client that you have. Like if you are delivering and your legal agreement tells about 99, then maybe you don't need to worry about higher. Yeah, but in the real life, yeah, we are looking at 999 or even 49s because it is also translating to the uptime of the overall system, right? And if you are breaking even if you are breaking latency SLA more than 99% of times, your overall system will not have very good statistics about its uptime. So we need to see, like for example, DataStax Astra Cloud service, we are looking at higher 999 or even 49s. But so there are some business use cases that even average is enough, right? If you have batch processing, so focus on throughput, not latency, it's often enough to look at the average latency. You are interested how many events are you able to process in some batch, so average is a good measurement there. But in the latency sensitive systems, then you need to look at the latency. Streaming systems in real time.